Hi everyone, my name is Jegason Diviant. I'm a developmental psychology PhD student. I'd like to present to you about the development of a narrative-centered learning game called SciStory Pollinators. This project, which was a collaboration between Indiana University, North Carolina State University, and University of Illinois Urbana-Champaign, traces the development of a narrative-centered learning game designed to support socio-scientific inquiry and persuasive writing skills for middle school learners. Throughout this presentation, we'll focus on how AI-driven conversational agents were developed to support student-led socio-scientific inquiry and the tensions the design team explored while integrating these agents into a complex community narrative. The target group for this design was 5th through 8th grade students in the Midwestern United States. The design team frequently needed to reorient their design choices by attending to what would be feasible in technology-scarce environments. They were designing for middle schoolers in resource-limited schools, dealing with issues such as limited internet bandwidth and student laptops with limited processing power. The socio-technical constraint was a primary driver for the design. The gameplay revolves around a socio-scientific issue with no correct answer, deciding how to use an empty community lot. Students must choose between supporting a community garden focused on food justice and pollinators, or parking structure advocated by City Park to attract local business. To manage this complexity, students utilize an in-game notebook, a cognitive hub where they can auto-capture character dialogue with a pencil button or draft custom notes. This allows them to systematically synthesize scientific evidence about pollinators with community economic needs before presenting their final argument to the mayor. The learning objectives were intentionally interdisciplinary. Rather than just testing science facts, the outcomes focused on scientific argumentation. The researchers wanted the learners to move past the surface level and engage in the process of identifying and evaluating evidence, recognizing that evidence comes from different sources, like scientists, beekeepers, and community activists, and must be synthesized into a persuasive claim. Ultimately, the goal of the researchers was that through playing the story game, students would develop a deeper understanding of how to integrate both community needs and scientific evidence into persuasive argumentation to help solve locally meaningful community problems. A fascinating pedagogical shift occurred early in the design. The team initially built a 3D world, but students became frustrated by its limited functionality. They expected traditional video game mechanics such as running and jumping and would often spend time trying to break the environment or roam outside boundaries. Additionally, the 3D version included an in-game text chat intended for collaboration, but students mostly used it for off-topic chatter. By pivoting to a 2D visual novel format, the designers purposefully removed these mechanics, distractions, and communication noise. This shift reduced extraneous cognitive load and forced students to focus on the core cognitive task, the conversation and synthesis of evidence. It emphasizes that inquiry-based learning, high-fidelity immersion, can actually be counterproductive if it distracts from the intended learning interactions. To scaffold this inquiry, the team deployed 3 distinct agent modalities: knowledge agents, feedback agents, and a helper agent. It's important to note that AI in this game is not a monolith. By siloing the AI into specific character roles, the designers created a scaffolding ecosystem. Technically, the team initially considered and used the FLAN T5 small model. This was a smaller, large language model used to interpret student input and match it with human written responses to eliminate the risk of hallucinations. However, they found that it required far too much training data to handle the natural variety of student ideas. Consequently, they transitioned to the Llama 3.1 8 billion model, While it has fewer parameters than GPT-4 Omni, the open source nature allowed them to keep all student data on private university servers, a critical ethical decision in the current educational climate, while providing more personalized and natural responses than the smaller FLAN T5 model. The true power of Gen AI here was enabling a guide, not tell philosophy. In previous years, an agent might just give a fact. Here, the feedback agent evaluates the student's argument and redirects them to another game character to find the missing evidence. This maintains student momentum while preventing cognitive offloading. The researchers' general design goal was to scaffold student inquiry without offloading the important cognitive work to the AI, positioning the agent as a catalyst for deeper investigation rather than a source of direct answers. Here we can see a specific example response from a feedback agent to a student. That's a good start. You mentioned that parking lots cause pollution and gardens are good for our air. To make your argument stronger, you can add more specific evidence. For example, you could talk to Nadia about how a community garden would help bees and other pollinators, or to Amra about the health benefits of locally grown food. Keep going. Despite the success of the feedback agents, the team encountered a significant help-seeking gap. Even though a helper agent, Tulip, was always available, students preferred calling for a human teacher. This illustrates a common problem in learning sciences. Students don't always know when they need help. In the section titled Challenges and Future Designs, the researchers reflect on a critical tension, balancing feedback and frustration. While students engaged in multiple rounds of revision, meeting the researchers' goals for deepening exploration, they encountered a frustration loop. This occurred when students would add detail to their arguments based on agent feedback, only to receive a nearly identical critique for a second or third time. The authors identify a key limitation here. The AI did not always acknowledge the nuance in students' improved responses. This nuance is essential for providing emotionally supportive feedback that both validates strengths and offers specific actionable improvements. This was largely a technical constraint. The team found that the Llama 3.1 billion model struggled with the high prompt complexity required to interpret multiple goals, conditional logic, and the structural depth of information simultaneously. Let's consider some of the key lessons from the researchers' findings. A primary lesson is that current mid-sized models used for data privacy reasons like Llama 3.1 billion struggle with the capacity for complex prompt interpretation required to recognize the subtle improvements in student work. This highlights a need for better emotional support in AI feedback, specifically feedback that notices when a student has made an effort to address a previous critique. As a solution, the researchers are exploring an alteration to the interaction structure itself. They are considering moving toward a back and forth style dialogue, similar to a text message exchange. This format would provide the time and space for more detailed comparisons between argument revisions. It would help students look back at their history, locate places for improvement, and feel more supported throughout the inquiry process. In terms of proposed revisions, I propose that these text-style cycles include metacognitive reflection cycles. By requiring students to justify why they made a specific change based on the agent's suggestion, we ensure the cognitive heavy lifting remains with the student. This keeps the regulation of learning human-centered, creating a hybrid environment where the AI supports factual scaffolding, while the teacher facilitates the deeper social and emotional work. To conclude, I want to synthesize some essential lessons that I learned from SciStory Pollinators. First, prioritize using AI to scaffold student agency through a guide, not tell approach. Direct answers from AI often promote passive consumption, so we must design agents to instead offer dynamic hints that point students toward evidence, encouraging them to discover the facts for themselves. Second, we must leverage multimodal digital learning environments to bridge the scientific with the social by providing students with diverse data types like hard pollination statistics and vital community perspectives, as an example. We can enable them to synthesize this complex information into an authentic, evidence-based argument. Finally, strategizing AI in educational games requires carefully balancing engagement with educational focus. In this study, the researchers intentionally utilized a simpler 2D visual novel format to successfully reduce mechanical distractions and keep students focused strictly on the primary inquiry tasks, whereas the 3D version of the game would have likely been a failure, as students tried to run around, find items, chat about unrelated topics, and potentially try to find ways to break the game. Furthermore, design strategies must proactively account for the technological limitations of smaller language models and the inevitable student frustrations they create, integrating active reflection and motivation prompts to help students navigate these predictable gaps. Thank you, and I appreciate any questions or comments you may have.